Unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
This is Week 2, Part 2. Today, we're really getting into the engine room of deep learning. We're talking about optimization, the crucial process of how a model actually learns from data. So we have our model's architecture, and we know how to measure its mistakes. But this all leads to a massive question. How do we actually train this thing? How can it possibly find the single best configuration for all of its internal settings, when the number of possible combinations is just astronomically huge? We're talking trillions upon trillions of possibilities. This, right here, is the core challenge we're going to unpack today. The way we approach this is to think of it as a journey. Imagine this vast mathematical landscape you see on the screen. Every single point on this landscape represents one possible set of your model's parameters, all of its weights and biases, and the height, or the altitude at any point, is simply the model's error, its loss. Our goal is to find the path to the absolute lowest point in this entire landscape. And that brings us to the fundamental challenge, which is all about the shape of this landscape. It's what we call a non-convex landscape. On this slide, you can see the ideal versus the reality. On the left, you've got this perfect, simple, convex bowl. Any step downhill is guaranteed to lead you to the one single best answer. But deep learning is, well, it's not like that. The reality on the right is this incredibly complex, high-dimensional, non-convex terrain. It's just littered with traps, countless local minima that look like the bottom but aren't, and treacherous saddle points that can stall our progress. This is the world we have to navigate. So let's define our objective mathematically. We want to minimize what's called empirical risk. Let's unpack the equation on the slide. L of theta is the total loss for a given set of parameters, which we call theta. To get this, we sum up, that's the sigma symbol, the individual losses for all n samples in our data set. For each sample I, the small l calculates the mismatch between our model's prediction, which is f of xi theta, and the true label yi. We then just average this total sum. Our entire goal is to find the one specific theta that makes this final L value as small as humanly possible. Okay, so how do we even begin this descent into the landscape? Well, we start with our most fundamental tool, good old vanilla gradient descent. Now, the blue line you see here represents batch gradient descent. It calculates the gradient using the entire data set. This gives a very smooth path, but it's incredibly slow and expensive. The orange line, on the other hand, is stochastic gradient descent, or SGD. It uses a tiny random sample, a mini-batch, to estimate the gradient. This makes the path look erratic and noisy, right? But here's the cool part. That noise is actually a feature, not a bug. It can help the optimizer jiggle its way out of those shallow local minima we talked about and find a better value. And the whole process is governed by this beautifully simple update rule. Let's look at it. Our new parameters at the next time step, theta t plus 1, are just our current parameters, theta t, minus a small step. That step is made up of two parts. Nabla LB of theta t, which is the gradient of the loss on our mini-batch, basically the direction of steepest descent, and eta, or eta, which is the learning rate. So all we're doing is calculating the way downhill on a small piece of data and then taking a small step in that direction. Simple as that.
Now, SGD is great, but that noisy path can be pretty inefficient. So we need to upgrade our toolkit to find a smoother and faster way down this lost landscape.
Which leads us to the obvious question. How can we actually improve on this noisy, often oscillating path that we see with pure SGD? The first huge improvement is an idea called momentum. The intuition is fantastic. We give our update rules some inertia, just like a heavy ball rolling downhill. So instead of only listening to the current gradient, we start to build up velocity from past steps. This helps the optimizer build up speed when it's heading in a consistent direction, and it smooths out all those noisy oscillations. It just powers right through the bottom of those long, narrow ravines. Let's look at the mathematics of this. It's a two-step update. First, we update our velocity, v. You can see the new velocity, vt plus 1, is a blend. It's part of the old velocity, vt, scaled by this momentum term, mu, plus the current gradient step. You can think of mu as controlling how much memory we have of our past direction. Then, in step 2, we update our parameters, theta, by simply adding this new velocity vector. That's it. This accumulation is what dampens the wiggles and speeds things up. Momentum is a big help, but it still uses one single learning rate, one step size for every single parameter in the model. But what if some parameters need big changes and others only need tiny adjustments? What if every direction in our huge, high-dimensional space needs its own unique step size? And this is exactly the motivation for what we call adaptive optimizers. The most popular one by far is Adam, which stands for Adaptive Moment Estimation. Adam is brilliant because it combines the inertia of momentum with an adaptive, per-parameter learning rate. It's become the default choice for so many problems because it figures out the right step size for each parameter all on its own. So let's quickly deconstruct Adam's update rule. It keeps track of two moving averages for every single parameter. First, there's MT, the first moment. This is just an estimate of the mean of the gradients. This is the momentum part we already know. Second, there's VT, the second moment, which is an estimate of the variance of the gradients. Now here's the secret sauce. In the final update, we take our learning rate eta and scale it by the momentum MT. But then, and this is the adaptive part, we divide it by the square root of the variance VT. So what does this mean? Well, if a parameter's gradient has been all over the place, its variance is high, so we take a smaller, more cautious step. If its gradient has been consistent, the variance is low, and we take a bigger, more confident step. It's a self-tuning learning rate. Having a powerful optimizer like Adam is fantastic, but sometimes the landscape is just so treacherous that even Adam can get into trouble. So we need some extra tools to help stabilize the whole training process. Just look at the effect of a technique called batch normalization on this slide. On the left, you have this chaotic, jagged, difficult landscape. On the right, it's the same landscape, but it's been dramatically smoothed out. Now that's a much easier hill to climb, right? Batch norm does this by recentering and rescaling the inputs to each layer during training. This basically prevents the data distributions from shifting around wildly inside the network. And the result is this much, much nicer landscape for our optimizer to work with. Think of these stabilizers as building a proper road for our journey. Proper weight initialization makes sure we start in a good place, on solid ground. Batch normalization is like paving the road, smoothing it out as we go. And for really deep networks, things like resonant skip connections act like express lanes, giving the gradient a direct highway to flow all the way back through the network without fading away. So far, we've been obsessed with finding the lowest possible point in our training landscape. But that's actually not the ultimate goal. The true goal of all machine learning is generalization. What really matters is how well our model performs on new data it's never seen before. And it turns out not all low points, not all minima are created equal. A sharp, narrow minimum like the one on the left might give you a great score on your training data, but it's brittle. A tiny change in the input data could knock you way up the side of that steep valley, causing a huge error. A flat, wide minimum, on the other hand, is robust. The whole area around it is also low error, so it performs well even on slightly different data. These flat, wide basins are what we're really searching for. And we can actually encourage our optimizer to find these flatter minima by using regularization. Let's look at the two most common types here. L2 regularization adds a penalty term to our loss function. You can see it's proportional to the squared L2 norm of the weight vector, W squared, which is just the sum of the squares of all the weights. This penalty discourages any single weight from becoming too large, leading to a more diffuse and robust model. L1 regularization adds a penalty based on the L1 norm, W1, which is the sum of the absolute values of the weights. This has a really interesting side effect. It tends to push many weights to be exactly zero, effectively doing automatic feature selection for us. So in the end, you can see that training a modern neural network is really a complete recipe. It's a synergy. You start with a well-designed architecture, you stabilize it with tools like batch norm, then you use a powerful optimization algorithm like Adam to navigate the lost landscape. And all the while, you use regularization to gently guide that search, not just for the deepest minima, but for the widest and flattest ones, the ones that will generalize well to the real world. And this brings us to a final and, I think, crucial question. This whole search process is incredibly powerful, but it's also computationally immense. It takes a huge amount of resources. So as these models get bigger and bigger, we have to ask ourselves, how do we balance the enormous cost of this search with the critical need to build AI that is responsible, efficient, and accessible to everyone?